Hello, Professor Brian back with another installment of problem solving, and this particular installment will be about moles, conversions from and to moles, and conversions to atoms and mass. So, given the review packet, there's a couple different questions that involve conversions using Avogadro's number as well as conversions using the molar mass of a given element. So, when looking at the periodic table, we have to remember that Z, the top number, is the atomic number. And that number tells us the number of protons and the number of electrons in the ground state. And this is just a little bit of review. The symbol obviously is the symbol associated with the name of that given element. And generally at the bottom of the periodic table, we see a value for average atomic mass. In the case of, let's say, carbon, you have something like 12.01 as a value. What is that? That is the mass of 1 mole of that element. And that unit is grams per mole, as shown here. Now, what is implied within this calculation is that we have 6.02 times 10 to the 23rd atoms are equal to the average atomic mass, right? Because 6.023 atoms is Avogadro's number, and that is equivalent to 1 mole of a given substance, right? So as a quick review, that is implied in this calculation of grams per mole that exists here in your periodic table. So the question asked us specifically, if we had 1.45 times 10 to the 25 atoms of aluminum, how many kilograms of aluminum would we have? Now, I suggest in all cases to try to utilize dimensional analysis to answer your questions, particularly when dealing with mass to mole or atoms to mole or atoms to mass. Whenever you see atoms, it is likely that you are going to have to convert to moles first, because that is how we packaged atoms in chemistry, meaning that Avogadro's number will be utilized. And the arrangement of this conversion factor is always so that we can cancel the units that we are moving away from and get the units that we are interested in. And I'm going to just move this down here. Atoms of aluminum. And since kilograms is the unit that we want at the very end, we have to recognize that that's the last unit that we are going to leave. So to get from moles of aluminum to a mass unit, we need to utilize the average atomic mass as given on the periodic table as, I believe, 27. And I will quickly pull that up. And it looks like that will be 20. I apologize. It's a little difficult to find this. It's 26.98 grams per mole. And we should recognize that to convert to kilograms, we need 1 times 10 to the negative 3. So again, what did we do here? We took the number of atoms. We used Avogadro's number to cancel away from atoms, leaving us with moles. We then converted away from moles by using the average atomic mass. And then the last step is just a simple conversion via prefix to get us to kilograms. If we were to put all of this now in our calculator, we end up with 1.45 e to 25 times 26.98 times 1 e to negative 3, all divided by Avogadro's number. And we have approximately 0.6499 kilograms, or as I would like most students to utilize, 6.50 times 10 to the negative 1 kilograms of aluminum. So that is a conversion from atoms to grams. Now, going back to the question about iron, it is giving us a volume of iron at 100.0 centimeters cubed, and they want us to determine moles of iron. Well, that's a very good question, because we need to utilize a conversion factor to get us from volume of iron to moles of iron. And how do we do that? Well, remember that a volume in centimeters cubed is the same as a volume in milliliters. And that's just a little review. These are equivalent. However, we should realize and remember that the best way to relate mass and volume is that mass is proportional to volume directly through density, equaling mass divided by volume, big V. So, being given a volume, we must convert using the density, and I have already looked that density up, and that density looks to be 7.874 gram per centimeter cubed. So again, I'm going to show you that you can do all of this in dimensional analysis times 10 to the 2 centimeters cubed of iron. Multiply that by the density, 1 centimeter cubed, and 7.874 grams of iron per centimeter cubed. But we are not done, because we can move from grams to 1 mole via the atomic mass of iron, which is 55.85. And now we have a two-step problem to get us the value we are looking for. 1 e to the 2 times 7.874 divided by 55.85. And it looks like we have 14 0.10 moles of our friend iron. And what did we do here? Again, as a recap, we took a volume, knowing that volume is directly proportional to mass. Using the equation of density, we can look up the density and maybe you will be given the density in a question on an assessment. And being given the density, you can utilize dimensional analysis to solve this problem by canceling again units of centimeter cubed, units of grams, and leaving yourself with moles. Recognizing that each one of these conversion factors is in fact a equivalency, and we should recognize where we get these from, right? This, the periodic table, and this is a intensive property that can be looked up. All right, again, if you have any more questions, feel free to drop me a line.